Thanks for the introduction, and thanks for all my great co-authors. Sorry. Let me get started with an overview of our results. So our contribution can be divided into two parts. The first one part, it is the GMW design, FS design-based framework of digital signature, which is Goldrich, Macaulay, Wilson, and Fair-Shamir transformation, but based on abstract group actions. So our contribution can be divided to two parts. The first part is related to the quantum random oracle model. So we distill the properties for the group action to be secure in the QROM. And the second part, we adapt the abstract group action into the construction of the Bullions, Carter-Smata, and Pinto paper ring signature scheme, but with the general linear group actions. And we also look at the concrete setting. So we instantiate our result on the alternating trilinear form equivalence. Specifically, we prove the ATFE-based signature. We provide some supportable evidence to its QROM security, as well as we implement the ring signature scheme. So let me get started with group action and the lotion. So yeah, group action is you can view it as a map of function. So given a group G and a set X, we can define a map from G cross X to X. And of course, you need to satisfy identity and compatibility. And another definition is for the orbit. The orbit is actually a subset of the set X for the every two elements in one orbit. So we can find there exists a group element G sends one to another one. And stabilizer group. Stabilizer group, if we fix one set element X in the set X, and we say the stabilizer group of this X, it is for every elements in the stabilized group, these elements will send X to the X itself. We also have some relations of the size of orbit and the stabilizer group. So by the orbit stabilizer theorem, we have the size of orbit times the size of stabilizer group is equal to the size of group G. And yeah, we can naturally define a stabilizer problem. So it's a computational problem. So given we fix one set element X, the problem is to ask to find such non-trivial group element G, which sends X to the self. And for the cryptography assumptions, we can define one-way assumption and the pseudo-random assumption. So for one way, it's we random sample X and we random sample Y in the on the same orbit of X. It asks to find, we assume no polynomial time algorithm to return such group element G, which G sends X to the Y. For the pseudo-random assumption, so it is, we assume is a stronger assumption. We assume there is no algorithm to distinguish the random distribution and the pseudo-random distribution. For the random distribution is that we sample two elements from randomly from X. For the pseudo-random, we just sample one randomly and another one we sample from the orbit of X. Okay, so how to use GMW plus FS to framework to design a digital signature is clear two steps. First, we have a GMW zero knowledge protocol, and we can use Fair-Shamir transformation to turn identification scheme to a digital signature. For the group action-based GMW zero knowledge protocol, we have two elements. X, Y is our public key, and we have a secret key G, which sends X to Y. And the protocol is as follows. So Alice random sample another group element H, which sends X to Z. Here Z is commitment, and then Bob random sample a binary challenge, come back to Alice. If challenge 0, Alice will send H, respond H, otherwise will respond HG inverse. And in the verification phase, Bob just need to check whether the response sends either X or Z to X or Y to Z. And then we can use via Shamir transformation turns that zero knowledge protocol to digital signature. The key idea is to use a hash function to simulate the interactive procedures. And for the security proof, in the random oracle model, there is a proof in 1996. For the quantum random oracle model, there are two concurrent work in 2019. So we focus on some concrete group actions in the list call for additional PQ signatures. It is based on the group action in the general linear group, which is math, less, and alter. So which based on matrix code equivalence and linear code equivalence and alternating trilinear form equivalence respectively. Very interestingly, these three problems are highly related. Because we have matrix code equivalence is basically polynomial equivalent to the alternating trilinear form equivalence. And the linear code equivalence, we can reduce it to these two problems. And one thing I want to mention that here the group actions in the general linear group are not transitive. Okay, so how to prove that security in the QROM? Here there are two key properties. One is the perfect unique response. So we say that a sigma protocol, which is a perfect unique response, if there are no two valid transcripts, ACR and ACR prime, we have the same challenge but different response. And also we can define the computational version. So we assume there is low polynomial quantum adversary to produce such two valid transcripts. And yeah, based on the QROM work I mentioned before, so it's straightforward. If we have perfect unique response, and one way is we can prove the group action under the GMW plus FS framework. Digital signature is secure under QROM. And we also can have the tight security proof under QROM based on work called Scifish. So appear in PKC20. We need to assume the computational version, and also we need a stronger assumption is pseudo-random assumption. Okay, so we distill how does group action satisfy perfect unique response and computational unique response. The first one, we need the group action. Here I assume we start with a fixed set element. So we if and only if we have this element, it has a stabilizer group, it is trivial. So it just means automorphism group is trivial. Also, for the computational unique response, we assume there is no polynomial time quantum algorithm can solve this stabilizer problem. That means low quantum algorithm, low polynomial quantum algorithm to find non-trivial automorphism. Okay, so next part is ring signature. We basically follows the Buelen's, Katsumata, and Pinto's design. This is very beautiful algorithm. So I will just briefly describe the verification phase here. So if you can say we have, if challenge 0, So our aim is to if we have x0 to xn, there are public keys we want to utilize this public key and the response to get the root. So if challenge 0, our response is HGI and pass and beta I. So if we have HGI, we start from x0, we can get xi, and sorry, we can get yi. If we have bit I, so we can get ci here. And then if we have the pass is the authentication path in the Merkle tree, so we can get the root. Otherwise, if challenge 1, we have the response H and bit 1 to bit n. So because of x1 to xn is all public, if we have H, so we can have yi to yn. If we have all the bit, so we have the C1 to Cn. And we can build the Merkle tree by itself, and then finally we also get the root. And I need some optimization method here, like unbalanced challenge and adding sort or velocity tree. So yeah, if you are interested, I recommend to write this very beautiful paper. Okay, so let's look at a concrete setting. It is alternating trilinear form. So what's the trilinear form, which is actually a mappable function from fq to n cos fq to n cos fq to n to fq. If it is trilinear, if all the 3 arguments is linear, and alternating it is if whenever 2 arguments are the same, when the phase is equal to 0, so we say that is alternating. And we can actually define a group action of the alternating trilinear form, which is we sample random invertible matrix from general linear group. And we can use this A act on the phi, that is A act on all the 3 arguments. Also, we can define a problem. So the problem is that we are given 2 alternating trilinear form phi and psi. The problem is asked to whether there exists a invertible matrix since that psi phi. Okay, so for this concrete setting, we use global basis to verify, or we provide some experimental support evidence to support the QROM security for the alternating trilinear form. We can set A and B to be 2 variable matrix, and B is A's inverse, and we can set up polynomial equations. So firstly, cubic equations, we can put A on the left side or B on the right side. And also we can have some quadratic equations, so we can move B to the right side and move 1B to the right side. So we have some quadratic equations. Also, we have some homogeneous equations. So we have AB equal to identity, BA equal to identity. For the global basis, if we directly use global basis, is very, very expensive. So we use the hybrid global basis. That is, we guess 1 row or 1 column for A. So we have the total cost is Q to the N times polynomial. So here Q to the N comes from the guessing cost. Okay, so yeah, we did the experiment on some small parameters. Like for Q is equal to 2, N is 10 and 11. All 100 samples return trivial stabilizer groups. For Q equal to 3 and N equal to 10 and 11 is also 10 samples return trivial stabilizer groups. And here is our implementation for the ring signatures. Here are some performance. So we also have the logarithm signature size. So if you can say the participants, if exponentially increase, our digital ring signature size increased linearly. Okay, so let me end by two open questions. The first one is we actually don't have the QROM security for such ring signature. So it's still open. And second one is we just have some experimental support or evidence for the stabilizer group is trivial. So for the rigorous proof is still open. Thanks for the listening.
Yeah, thank you for the interesting talk. Has anyone got any questions? No? Okay, good thing that once again I do. So you were talking about this trilinear form-based group action. It's difficult to decide if this stabilizer group is trivial or not. Do you have any intuition on if that stabilizer group turns out to be non-trivial, if the associated computational problem, do you expect that to be hard?
Sorry. So the trilinear form equivalency is hard or not. It depends on the stabilizer. Yeah.
All right. Well, let's thank Gong again.